Can you see the screen? Is it visible to you? Are you able to see the screen? Okay, Akshara. Okay, okay, Adarsh. So, do you remember where we stopped last class? Which section we were taking? We were discussing solution of non-homogeneous recurrence relation. Solution of non-homogeneous recurrence relation. And in non-homogeneous, you know, when the non-homogeneous equation means, suppose you have a n minus 1 plus 2 into a n is equal to, if it is 0, then it is homogeneous, but if it is a function of n, then it is non-homogeneous. If this is not 0, then it is non-homogeneous. So we have different cases when we look at this non-homogeneous part. If this is a constant, say 1 or 2 or any constant value that it does not involve this n term, if it is a constant, then we have discussed the method to solve this, isn't it? If it is a non-homogeneous recurrence relation, and if the RHS is a constant, if RHS is a constant, then we had seen how to solve it, isn't it? That was a case 1. This was case 1, isn't it? Do you remember how to solve it? How to solve in this case 1? Anyway, for non-homogeneous, we have two solutions. That is the general solution, an is equal to an homogeneous plus an particular solution. You know how to solve homogeneous. Just put this right hand side is equal to 0. An minus 1 plus 2 into an is equal to 0. This becomes homogeneous. And then you solve for the homogeneous part. Just we had discussed in the last section. The next is the particular solution. It is this particular solution that depends on the value of RHS. If it is a constant, then you have to put, that is case 1. Case 1, if f of n, this RHS, we can consider it as a function of n. And if f of n is equal to a constant, then our particular solution, an of p is equal to what? You have to put p, isn't it? In this given equation, this is the given equation, you have to put an is equal to p in the given equation. If and when we put an is equal to p, if the rule fails, that is, if suppose you get this 0 equals 1, or if the rule fails, is equal to np. And if again the rule fails, you put an is equal to n square p, and so on. Most cases this will evaluate to true only. So you will get the value of p from here, and you can substitute it in this equation. So this is the first case. Then second case is case 2, when you get a polynomial. F of n is a polynomial, isn't it? When f of n is a polynomial, say an minus 1 plus 2an is equal to n square plus n plus 1. Okay, so there is a polynomial on the right hand side. Then what our particular solution, an of p is equal to, the form is, we have written as d0 plus d1n plus d2 n square. and or instead of d0 d1 d2 you can also put p1 p2n plus p3n square. Any constant term can be put. So since it is particular solution you can use constants p1 p2 p3 etc. And or you can even put d0 d1 d2. We had solved with d0 d1 d2, but even you can use other constant values or terms like p1 p2 etc. and find out and solve this sections, this equation. That is, if you put an is equal to this thing, then you have to find out what is an minus 1. That is p1 plus p2 into n minus 1 plus p3 into n minus 1 the whole square. So you get the an minus 1. You substitute in this equation for an minus 1. And finally, you compare the coefficients on the left hand side and right hand side and equate the coefficients. You get the constants p1 p2 and p3. Okay, this was the second method when a polynomial appears on the RHS. So this we had seen in the last class. Then next we are moving on to case 3. Case 3. Did all of you join? So moving on to case 3. Or I think we'll do one more example. And before going on to case 3, let us do one more example in the previous section. In case 2, okay. Case 2, question 2. Second question in case 2, okay. Solution of non-homogeneous equation, case 2. We were discussing about case 2, that is when a polynomial, when f of n is a polynomial. Now here we are going to do the second question. Now write the question, find the particular solution. Find the particular solution. Find the particular solution of the recurrence relation. Find the particular solution of the recurrence relation AR plus 5AR minus 1 plus 6AR minus 2 is equal to 3R square minus 2R plus 1. So this is the question. This is the recurrence relation given. Okay. This is the recurrence relation. So what is the question? Which solution should you find here from this recurrence relation? Which is the solution that you should find as per the question? Is it homogeneous or non-homogeneous? Is this equation homogeneous or non-homogeneous? Is it homogeneous or non-homogeneous? Come on. Non-homogeneous. Why? Because this RHS is not 0. And now if it is not 0, then you should look at this RHS and find out what is it. This is f of n. This is our function f of, here it is r. The term is r, so it is f of r, isn't it? The variable used is r, so it is f of r. Looking at the function, we find that it is a polynomial of degree 2, isn't it? It is a polynomial of degree 2. That is, f of r is equal to, just write like this. Here, f of r is equal to 3r square minus 2r plus 1. Okay, and we are asked to find, now for any non-homogeneous recurrence relation, we have two solutions. One is homogeneous solution and the other is particular solution, isn't it? For any recurrence relation an, you have an homogeneous plus an particular solution. Two solutions. And here instead of n, the variable given is r. So it just like write ar is equal to ar of h plus ar of p. So Here we are asked to find, the question says only to find the particular solution. We can find the homogeneous solution, we can find the particular solution. Finally, when we add them together, we get the general solution AN. This is the general solution AN. But the question says you need to find only the particular solution because this is a lengthy question. So you are asked to find only this part, the particular solution. So we needn't find the homogeneous part. The question says to find only the particular solution. Then you just need to find the particular solution. You needn't equate the left hand side to 0 to make it homogeneous and then find the homogeneous solution. You don't need to find this. You have to find only the particular solution as per the question. So let us see how to find the particular solution. Okay. Now, substituting substituting AR of P. See, look at this. What will be the solution? If it is a polynomial, what will be the particular solution AR of P? It is equal to, as we said, this is of degree 2, so it can be d0 plus d1, the variables are, plus d2 r square. If it is 3, if it is r cube, then you have to continue this and d3 r cube, etc. It goes on. So instead of d1, d2, d3 variables, I can also use p1, p2, etc. So for, since it is particular solution, I am going to use p1, p2, etc. So p1 plus p2r plus p3 r square. So instead of these variables, you can choose any variable, any name for the variable. Earlier examples we did it d0, d1, etc. Now I am going to use the variables p1, p2, p3, etc. Both are the same, only thing the name is different, but the form should be the same. That is, it should be of degree 2. Constant P1 plus a constant P2 into R plus another constant P3 into R square. That is our particular solution. This is the form of our particular solution if a polynomial appears on the right hand side. So after writing this particular solution, what our aim is to find out the values of P1, P2 and P3 and substitute in this equation. Then you will get the particular solution. So if we have introduced some constants, we have to find out the form of the particular solution. So let us see how to find the values of P1, P2 and P3. So substituting AR of P, AR of P is equal to P1R. Okay, let's start from the highest degree. Since we in polynomial we start with highest degree. So P1R plus P2 P1R square plus P2R plus P3. So polynomial we often write it from higher degree to lower degree. So just write P1R square plus P2R plus P3. This is the particular solution because our right hand side is a polynomial. Our right hand side is a polynomial. So this is a polynomial. So we have to write a particular solution correspond. Looking at the degree, we have to write the particular solution, and the degree of the particular solution will also be the same. So we are assuming that P1, P2 and P3 are the constants, and P1 R square plus P2 R plus P3 is the particular solution for this given recurrence relation. So now we have to find out the values of P1, P2 and P3. For that, okay, what we are going to do is, we are going to substitute this P1 R square plus P2 R plus P3 into the recurrence relation, into the given recurrence relation. What is the recurrence relation given? The given equation is AR plus 5 into AR minus 1 plus 6 into AR minus 2 is equal to 3R square minus 2R plus 1. This is the recurrence relation given. So what we are going to do is, we are going to substitute this into the AR. For this AR, we are substituting this polynomial here. Then for AR minus 1, we have to substitute, replace R by R minus 1 and substitute. So we have got AR as AR is equal to P1R square plus P2R plus P3. This is AR. So since the particular solution is of this form, we have AR of, since we know it is a particular solution, so you needn't write it. So AR is P1 R square plus P2 R plus P3. Now this term we have got. Now what next we have to find AR minus 1. AR minus 1 is equal to, just put R minus 1 in this equation, plus P2 into R minus 1 plus P3. So this is AR minus 1. Next we have to find out AR minus 2. That is AR minus 2 is equal to, in this equation just put R minus 2. P1 into R minus 2 the whole square plus P2 into, it's P2. P2 into R minus 2 plus P3. So we have got these three terms. AR is here, then AR minus 1 is here, then AR minus 2 is here. Okay, so first this AR we have to find out from the particular, looking at the particular, looking at the f of n, we have to write the polynomial form, and then from AR we can write AR minus 1 by substituting R by R minus 1, and by substituting R by R minus 2 you will get AR minus 2. So now what we are going to do is we are going to substitute AR minus 1 and AR minus 2 into this LHS. Okay, and we are going to solve the LHS. Finally, after solving the LHS, we will compare it with RHS, and then we are going to equate the coefficients of R square. You will get one parameter. When you equate the coefficients of R, you will get another constant P2, and when you equate the constants, you will get another term P3. So that is how we are going to calculate P1, P2 and P3. That is, in this equation we will be putting AR as this as this polynomial, AR minus 1 as this polynomial, AR minus 2 as this polynomial in the RHS. Finally we evaluate the LHS, sorry, this is LHS, evaluate the LHS, and then we compare it with the RHS, and for comparing we take the terms, that is R square terms will be compared together, then we compare the R terms on the left and right, and then the constant terms on the left and right. After these three comparisons, we will get the value of P1, P2 and P3. And once we get the value of P1, P2 and P3, we get the particular substitute in this equation, you will get the particular solution. So let us see how to find out P1, P2 and P3. So when I substitute it into LHS, I'm going to substitute AR minus 1 and AR minus 2 into LHS. Our LHS is AR plus 5 AR minus 1 plus 6 AR minus 2. This is our LHS. Now I'm going to substitute for AR. We had written earlier, AR is P1 R square plus P2 R plus P3 is AR, isn't it? Plus 5 into AR minus 1, we have written before, what is AR minus 1? P1 into R minus 1 square plus P2 into R minus 1 plus P3. Okay, this is AR minus 1. Next, plus 6 into AR minus 2. We have written what is AR minus 2 earlier, that is P1 into R minus 2 the whole square plus P2 into R minus 2 plus P3. So we are going to solve this LHS alone, and then we will get, we have to collect all the R square terms, R terms and constant terms together, because we have to compare it with the left hand side. So I had given this derivation in the course notes on page 28. Okay, the solution, I had solved it on page 28 of course notes. It's uploaded in Linbase. Okay, so you just refer page 28. I have solved this left hand side, and finally what I got is 21 P1 R square minus 34 P1 minus 12 P2 into R plus 29 P1 minus 17 P2 plus 12 P3 P3. This is what I got at the end. And now I'm going to equate it with the RHS. RHS is 3R square minus 2R plus 1. So I got all this. Solving means we have to expand all these. R minus 1 the whole square as A minus B the whole square is A square minus 2AB plus B square. Likewise, you have to open all the bracket, multiply everything together, and finally collect all these terms, R square terms together, then R terms together, and then the constant terms together, equate it to the RHS. And finally, now we are going to compare. So the R coefficient of R square on left and right. What is the coefficient of R square on left? I'm going to compare the coefficients of R square, R and constants. So, and the constant term. So the coefficient of R square on left and the coefficient of R square on right is equated. So what is the coefficient of R square on left? Comparing coefficients of LHS and RHS. First, we are going to compare coefficient of R square. What is the coefficient of R square? What is the coefficient of R square? 21 P1, isn't it? We have three constants. Our constants are P1, P2 and P3. We have to find the values of these three. Okay. Find values of P1, P2 and P3. For that, we are going to equate the coefficients. So, first we are going to equate the coefficient of R square. You get 20 minutes, 12 P1. Okay. What did I write here? Sorry, this is 12. Okay, this is 12. So when I compare the coefficients, I get 12 P1 on the LHS. It is equal to, when I compare it with the right hand term, see this 12 P1 is the coefficient of R square, and on the right hand side 3 is the coefficient of R square. So I can equate these coefficients together. I will get 12 P1 is equal to 3. Okay, 12 P1 is equal to 3. So 12 P1 is equal to 3. So P1 is equal to 3 by 12, which is equal to 1 by 4. So I got the value of P1. Next, second, I'm going to compare the coefficients of the next term. First we took R square, next we are going to compare the coefficients of R. Now what are the coefficients of R? Coefficient of R is 34 P1 minus 12 P2. This R on the left hand side, you get this as a coefficient of R, and here you get minus 2 as the coefficient of R on the RHS. So when we compare these two, you get 34 P1 minus 12 P2 is equal to 2. Okay, and we know the value of P1 as 1 by 4. So 34 into 1 by 4 minus 12 P2 is equal to 2. So what will we get? What will we get here? If you solve, what will be the value of P2? What will be the value of P2? 12 P2 is equal to 34 by 4 minus 2, or P2 is equal to 26 by 48, which is equal to 13 by 24. Okay, this is the value of P2 when I compare the coefficients of R. Next, we are going to compare the coefficients of, we have only the constant terms left. So comparing constants. The constant term here is 29 P1 minus 17 P2 plus 12 P3. We don't have any R terms here. If there are no R terms, it is constant, and that is equal to the constant term on the RHS is 1. So we are going to equate them together. Constants, that is 29 P1 minus 17 P2 plus 12 P3 is equal to 1. So we know the value of P1, 1 by 4 minus 12, 17 into P2. P2 is 13 by 24. We had found it now. Then 12 P3 is equal to 1. Now we know all the values. Solve this and find the value of P3. You get P3 is equal to 71 by 288. Okay. Now we have got all the three constants P1, P2 and P3. We can substitute it in the particular solution. Now substituting. Therefore, AR of P is equal to, it is P1 R square plus P2 R plus P3 was a particular solution since it is a polynomial. Since the right hand side was a polynomial, and we got the value of P1, P2 and P3 also. So now this becomes P1 is 1 by 4 R square plus P2 was 13 by 24 R plus P3 was 71 by 288. So this is our particular solution. Okay, so whenever you are asked to find the particular solution, write this general form and solve for P1, P2, P3. And to solve for P1, P2, P3, we have to substitute in the left hand side. We have to substitute AR minus 1, and because these are the terms given here, AR minus 1 and AR minus 2, we have to substitute on the left hand side and then compare the coefficients. So this is one particular form of the second case where you are asked to find only the particular solution. If you are asked to find the homogeneous solution, you have to find you have to equate this right hand side to 0 and find the homogeneous solution. Here you are asked to find only this particular solution corresponding to the RHS. So this is the procedure to find the particular solution. So since it is a polynomial, your particular solution AR of P will be a polynomial of the same degree, and you have to put constants along with those terms P1 R square plus P2 R plus P3 and solve for P1, P2 and P3. So this is one case of this is one problem related to second case. Now let us move on to the third case. Did you write it down? Did you write it down? It is there in the course notes. So you have to look at how I had solved it from your course notes and write it in your notebook. Okay. It is there in page 27. The question is there in page 27. Now let us move on to the third case, case 3. Solution of non-homogeneous equation, case 3. So first we had discussed when case 1 means f of n is equal to a constant. Case 2, f of n, that is the RHS, is a polynomial. And now we are going to case 3 when f of n is an exponential function. That is some number raised to n. Okay, example. So this is the third case. So case 3. Question. Solve the recurrence relation. Solve the recurrence relation. An is equal to 2an minus 1 minus an minus 2 plus 2 raised to n. This is the recurrence relation given to us. Solve the recurrence relation. So when you are asked to solve the recurrence relation, we have to bring all these terms, a terms to the right and see what is remaining on the left hand side. So when I bring all these a terms to the right, it becomes an minus 2an minus 1 plus an minus 2 is equal to 2 raised to n. So we find that the RHS is of this form, exponential form, a number raised to n. So this we have to solve in a different manner. Okay, so we find that what is the order of this equation? How do you find the order of this equation? N minus of n minus 2, isn't it? N minus of n minus 2. This highest and lowest suffix, when you minus it, you get the order. So these will cancel, the order is 2. So it is a second order. It is a second order non-homogeneous, because this side is not 0, right hand side is not 0. It's a second order non-homogeneous recurrence relation. Second order means it will have two roots, isn't it? Second order non-homogeneous recurrence relation, and its total solution. That is an. Total solution is the final solution or the general solution. An is equal to an homogeneous plus an particular. Okay. So for all these non-homogeneous equations, we have recurrence relations. The total solution or the general solution an is the sum of the homogeneous solution and the particular solution. So an of homogeneous plus an of particular solution. Now, homogeneous solution, we know as before, we have to find out in the same manner that we had studied earlier. By equating this RHS to 0, we can find the homogeneous solution. Then this particular solution, to find out the particular solution, we look at the form of this function appearing on the right hand side, and then we solve it. So if it is this exponential form, let us see how to find the particular solution. Homogeneous is the same throughout, but particular solution differs depending on this function. Okay, so the total solution is given like this. Now we have to find the general or the total solution. So to get the total solution, that is total solution is an is equal to an homogeneous plus an particular. Two solutions are there. Take the sum of these two solutions. So now let us take step 1. We are going to find homogeneous solution. This part an of h. Finding homogeneous solution. We are going to find the homogeneous solution. I hope you know we had done it many times to find the homogeneous solution. The equation, the question given to us is, what is the question given to us? an minus 2 into an minus 1 plus a into n minus 2. This is the RHS. And to find homogeneous solution, you equate it to 0. And then you write the characteristic equation. Write the characteristic equation. Write the characteristic equation, that is you replace a by r and raise it to the suffix n minus 2. Then a replaced by r, raise it to the suffix n minus 1 plus a by r, raise it to the suffix, you get n minus 2 is equal to 0. Next, divide by this lowest power throughout and you get r raised to n minus r raised to n by r raised to n minus 2, you get r square minus 2r plus 1 is equal to 0. Isn't it? Now find the characteristic roots. Find the characteristic roots. What are the roots? Now find the characteristic roots. What are the roots? Come on first. What are the roots? What are the roots corresponding to r square minus 2r plus 1 is equal to 0? You are just solving a homogeneous part. You write the characteristic equation, find the roots. What are the roots? How do you find the roots? R is equal to minus b plus or minus root of b square minus 4ac by 2a. So here a is 1, b is minus 2, c is 1. And substituting, isn't it? A is 1, b is equal to minus 2 and c is 1. And you get the root r is equal to What did you get? 2 plus or minus root of minus 2 the whole square minus 4 into 1, 1 into 1. Yes, very good. 1 by 2 into 1. You get it to be 2 plus or minus root of 4 minus 4 by 2, and that is equal to 1. This becomes 0. 2 by 2 you get 1. So this is the root. Okay, Typhon. So you have a single root, but since the order is 2, you have two same roots. There will be two roots, and both roots are 1. That is, if you have two same roots, same distinct, same real roots, it's not complex, it is same real roots. Then the solution, how do you find the homogeneous solution? An of h, the homogeneous, if you have same roots, both the roots are the same, your degree is 2, so you have two roots and both the roots are 1. If you have same roots, then you had studied the formula for the same roots. What is the formula if you have two same roots? C1 plus C2n into r raised to n, isn't it? C1 plus C2n into r raised to n is the homogeneous solution if you have two same roots. Okay. Or I had given in the note like this: an of h is equal to, you have I'm going to expand this equation, c1 r raised to n. I'm going to multiply with r and throughout, c2 n into r raised to n. Okay, so instead of C1 in the notes, I have given it as A, and this instead of C1 and C2, I have given it as A and B. And this R, instead of the root 1, R, I had given it as alpha 1 and alpha 2. Okay, alpha 1 raised to n plus B into n into alpha 2 raised to n. Anyway, alpha 1 and alpha 2 are 1, both are same. Okay, A into alpha 1 raised to n plus Bn into alpha 1, since alpha 1 is equal to alpha 2, we can write here alpha 1 itself. Okay. Both roots are same. So either you can go for this one, or easy method to remember is an of h homogeneous C1 plus C2n into r raised to n. If the two roots are same, it is C1 plus C2n into r raised to n. This formula you should study. Okay, you should study this formula. When two roots are same, this is the formula to be applied, and the constant here are C1 and C2. Okay. In the notes, I had taken it as A and B. Instead of C1, C2, I had given it as A and B. And instead of R, I had written alpha. Alpha 1 raised to n. Because you have same root, you have alpha 1 raised to n on both terms. So anyway, let us take this one. An of h is equal to C1 plus C2n into R raised to n. Okay. So now the given initial conditions. I think I forgot to give you the initial conditions. If you don't have the initial conditions, then you can stop with this. Okay. If you don't have any initial conditions, then you needn't find the value of C1 and C2. But if you have the initial conditions given initial conditions, then you have to find the values of C1 and C2. Given initial conditions are A0 is equal to 1 and A1 is equal to 2. Now the next step, what you have to find is substitute for n is equal to 1 in this equation. Substitute for n is equal to 0 and n is equal to 1 in this equation, and then you have to find out, this is our equation 2. Okay, substitute for n is equal to 1 and n is equal to 2 and find the values of constants. Substitute n is equal to 0. Okay, in equation 2, you get A0 is equal to C1 plus C2 into n, isn't it? N is 0 into R is 1, R raised to 0. So that is A0 is equal to, this term becomes 0, n number raised to 0 is 1, so we get C1, and C1 is equal to A0 is given to us, and that is 1. So you have to find out, then substitute for n is equal to 1 in equation 2, you can find out the value of C2. And then if you substitute, after finding the value of C2, if you find the substitute in this homogeneous equation, you will get the homogeneous solution. You substitute for C1 and C2. Okay, I hope you can solve that part and find out the homogeneous solution. Okay, then next class we will go to particular solution. Say your attendance.
1.
2 absent. 3 3 3 present. Absent. 4
4, 5,
6.
7, 8,
9,
10,
11,
12,
13,
14 absent.
15.
18
18, 19,
21, 24,
23
23, 24,
20. Okay, 24 present. 25
26,
25 absent.
26,
Okay, 26 next.
27, 28,
27
28,
25 undo. 26 present. 27 present. Then 28
28,
29 present.
30, 31,
Okay, 31 32 present. 33 33 absent. 34 absent. 35
35,
36 okay, 33 36 absent. Okay, 36 present. Next 37 37 absent. 38
38,
39 absent. 40 absent.
41,
41
42,
43
44,
present. 44
45, 46,
48.
40
49,
40 48 present. 49 49 present. 50 50 present. 51 51 absent. 52
52, 53,
54.
55,
56,
57, 59,
58 present. 59
60,
60 61,
61.
62, 63. Okay. Absentees number 3, 25, 34, 39, 40, 34 present, 39, 40, 51. Okay. Thank you.